All right, we're going to conclude section 14.4 in this video, and we're going to do number 16 on page 936. Page 936, number 16 says, in exercises 11 through 19, evaluate the integral, the triple integral over d of x plus z dv, where d is the solid region bounded by the cylinder x squared plus z squared equals 1, and by the planes y equals -4, y equals 5, x equals 0, and x equals 1. All right, so here for this one, I am going to go ahead and sketch our three-dimensional region D over which we're integrating. And it's just because I want to point out that this region D is of all 6 of the different types of triple integral regions we have. All right, so we are bounded by a cylinder, and that cylinder is a cylinder that runs along the y-axis and has radius 1. And then we're also bounded by the planes y equals -4, y equals 5, x equals 0, which is the YZ plane, and then x equals 1, which is right at the edge of the cylinder that we have. So let's sketch that portion of the cylinder. So it doesn't, because it's bounded by x equals 0, it's not going to go into behind the YZ plane. So let's just do this. And it's also bounded. Is it bounded by anything else? I lost the question. Hold on, bear with me 1 second. Bounded by the cylinder and by the planes. Okay, so we are not bounded by the plane z equals 0. I was just trying to see, do we have a quarter cylinder? We have a half cylinder, so we have a half cylinder here. So is this is not of all 6 types. So we're gonna have a half cylinder, something like this. And this is at, what was it, y equals 5. It gets cut off, so that's 5 right there. And then over to this side, -4. So this one's not actually of all 6 types. If it were a quarter cylinder, it would be. And then a straight dotted line right there because it gets cut off there, and that back there is 4. So let's put a little 4 right, or -4, excuse me. -4 there. So now we have what we had done in previous problems is we projected into the XY plane. And notice why now maybe this one's probably useful in why I use the, actually we could do this as a bunch of different types. I'm not going to do it a couple of different ways though. But I use the term smash, which of course doesn't seem like a technical term, and it's not a technical term, of course. But if, say for instance, we want to take this thing and we want to put it into the XZ plane, that's why I say smash, because we're going to come from the left and the right and kind of put it into that plane right there. If we want to do the XY plane, we would have to come from the top and the bottom and push it down and push it up into that plane. So we can do this a number of different ways. So let's look at probably the most intuitive and natural way to do this is to actually take it and push it back into the YZ plane. So what you oftentimes want to look for is what's going to give you the simplest setup. And if we push it back, then we would, instead of looking at top and bottom, we would be looking at front, which we can easily solve for the front of the cylinder, and back, which the back of the cylinder is just x equals 0. And then from there, we would just, our region, once we smash it into the YZ plane, our region is just a rectangle, which is a very simple region to work with. So let's just start there and look at, instead of top and bottom, we're looking at front and back. So front, the front of this thing, if we were to solve it, remember this has the equation x squared plus z squared equals 1. So this is x squared. So we would solve for x in that scenario. And if we take x squared plus z squared equals 1, and we solve this for x, and notice we're just going to be looking at the positive x because x is, this thing is bounded at the back by x equals 0. So this would give us x equals the square root of 1 minus z squared. That would be our front. And then our back. And remember, all this is bounds. We're not doing integrand at all. They give us our integrand. So we're figuring out the bounds for all of this. Put it in bounds. So then our back is just going to end up being x equals 0. Now, once we do that, now we have to look at what are the quote unquote sides. We take this and we smash it back into the YZ plane. So what is that going to look like if we do that? If we do that, the sides, and now you also see why I put sides in quotes. So we will be in the YZ plane. YZ, and if we push this back, once we do that, it's just going to look like this. So that's not to scale, but we'll pretend it is. Where this is 5, this is -4, this is 1, and that's 1. So then when we push this thing back, we get that region right there. And then we look at this and we say, okay, is this right here a type Roman numeral 1 or type Roman numeral 2? It's actually both. So whenever I push it back, and these numbers that I use to name these things are not like anything official. It's just to kind of keep our different types in order. So whenever I push back, I call going front and back, I say type Arabic 3, Arabic numeral 3. So type 3. And then we know that this is both, this region right here is both 1 and 2. So 1. So type 3, comma 1. Arabic mean Roman numeral 1 or Roman numeral 2 is what we would call this region. So now let's set up our region D and then set up our integral from there. So D is equal to the set of points x, y, z, such that now we're always going to start with this part, not the front and the back. That's going to be the last thing because that's the part that that can be a function. They can both be functions of two variables. So let's say we go from constant to constant. It doesn't matter. We go from constant to constant in this y direction here. So y varies from -4 to 5. And then our function of one variable to a function of one variable, it just so happens those functions are constants. Oops, that's -1. Our z goes from -1 to 1. And then from function to function, you always want to be going in the positive direction. So we're going to go from back to, so we're the smallest x value to the largest x value. So the smaller x value is x equals 0. The larger x value is x equals, or x values are x equals 1, square root of 1 minus z squared. So x goes from 0 up to the square root of 1 minus z squared. That's our region D. Now we can set up our triple integral, or iterated integral, excuse me. So -4 to 5, and then -1 to 1, and then from 0 up to the square root of 1 minus z squared. And our integrand was, I didn't write down the problem. x plus z. And these are x's, so that's dx. These are z's, that's dz. And these are y's, that's dy. All right, let's look at this quickly one other way. Let's look at taking this, since we haven't done one of those. We've done smashing everything into the xy plane. We just went back into the yz plane. Now let's go into the xz plane. And then you all can try to evaluate both of these integrals and see, do you get the same thing? So let's look at our picture first. If we go into the xz plane, then when we smash this thing into xz plane, what is it going to look like? And in that scenario, we're not looking at top to bottom, nor are we looking at front to back. We're looking at left to right. So now if we do it another way, then our bounds, the left-hand side would just be y equals -4. The right is going to be y equals 5. So the left, y equals -4. The right, y equals 5. Now our quote-unquote sides, we'll sketch that. So if we take this thing and we smash it into the xz plane, what is it going to look like? So our x and our z, no, actually, this I don't need. This I do need to extend. I extended those the wrong way, so that's z. This needs to come down. So our x is on, we're on the positive side, but our z is both positive and negative. So now if we take this thing, our sides, this is what our sides look like, where that's 1, and that's -1. And this would be our side region. And now we can look, what's the easiest way to do this? Go from function to function in the x direction would be the easiest way to approach that. So when we do that, normally, so this would be, if we were going from function to function and we were going up, that would be a type Arabic numeral 1. But since we're going right, that's going to be a type, we're going to go this way. So that's a type Arabic numeral 2. And when I go left and right, I call this type Arabic numeral 2, then comma, going this way, Roman numeral 2. Now, our function on the left is just x equals 0, and our function on the right is x equals the square root of 1 minus z squared. So our region D here, so let me just label it here so we have it labeled in our picture. X equals 0. Over here, x equals the square root of, what was it, 1 minus z squared. And now we'll put we have our left and our right. We have our constant to constant. And our left and our right is really our function of 2 variables to function of 2 variables. It's okay if a function of 2 variables just happens to be a constant. Our function of 1 variable to function of 1 variable is x to x, and our constant to constant is z to z. So now our region D in this scenario would be D equals the set of points x, y, z, such that we're going from constant to constant in the z direction. So -1, z went from -1 to 1. Function of 1 variable to 1 variable in the x direction. So from x went from 0 up to the square root of 1 minus z squared. And then we go from function of two variables, a function of two variables in the y direction, and it went from -4 to 5. So that's our region D. So now our iterated integral, constant to constant, -1 to 1, function of one variable to function of one variable, 0 to square root of 1 minus z squared, and then constant to constant. I'm sorry, function of two variable, function two variable. It just so happens that they are constants, -4 to 5. And our integrand again was something x plus z. These are y's, so that's dy. These are x's, so that's dx. And those are z's, so that's dz. So evaluate those two integrals in those two ways and see that you get what you should, unless I botched something somewhere, which I don't see that I did. You'll get the same two values regardless of which way you set that up. All right, so one last note for this section that you'll need to know is, given the solid region D, the volume of D is given by V equals the triple integral over D of 1 dV. So similar to how we would find the area with double integrals for a triple, if you have a region D and you want to find this volume, you set up the iterated integral, and then your integrand is just 1 for that. All right, so that concludes section 14.4, and we'll start section 14.5 in our next video.